To quickly review what we've been doing so far on VCOs. Last class we finished up the linear time variant model, the Hajimiri-Lee model. Okay, we figured out the expression for the noise in the thermal region, and similarly the 1 over f cubed region also. So we figured out the noise in the 1 over f cubed and the 1 over f squared regions. Okay, and we said primarily it depends on two things. It depends, the overall noise profile depends on the impulse sensitivity function, first of all. Okay, in other words, how sensitive the oscillator is to when the noise is injected into the tank, okay, into the system. And number two, it also depends on the symmetry of this impulse sensitivity function. For example, the 1 over f cubed noise can be reduced if you make this more symmetric. Okay, and we also looked at how you start off designing the VCO, right? Just starting off from the frequency of oscillation is not going to be enough, right? We said initially f0 is 1 over 2 pi root LC, but that does not tell us anything about L and C, right? It does not tell you what value of L to start off with or what value of C to start off with. Okay, a better way to do this is to start off with the amplitude. You know that you want maximum amplitude from the VCO, and you know that the amplitude is a function of the bias current and the parallel resistance of the tank. So to first order, you're going to assume that all this parallel resistance comes from the inductor. Okay, and we said that this Rp is more or less proportional to the value of L. Okay, even if the Q changes, it changes very little compared to the actual value of the inductor itself. Okay, and you are going to have a maximum, an upper limit on the total amount of current you can use for your VCO. So based on that, you choose the right value of Rp and inductor such that you are in this portion of the curve, right, in the knee portion. We said if you actually plot the output impedance as a function of IT or Rp, what happens is eventually the output amplitude keeps increasing till a point where it actually saturates, because there are certain fundamental limits. On the upper side, you don't have a limit in this kind of NMOS only oscillator, but on the lower side, you do have a minimum VDSAT requirement for the current source, for example, and the cross-coupled transistors. Okay, so your best option is to actually operate in that knee region. So you are going to choose IT and Rp such that you operate in that region. Then the next step is to choose the value of C which will make you oscillate at your desired frequency. Okay, and design your cross-coupled pair such that you have a certain startup gain, right? You know the bias current, you know the startup gain you want to achieve, therefore you can find out the width of the transistors. What about the length of the transistors? You would start off with minimum length, obviously. If you use any larger length, you are just adding unnecessary parasitic capacitance to the output nodes across the tank. There are certain cases when you might need to use a larger length. For example, if you have made the ISF as symmetric as possible and you still see 1 over f noise coming from the cross-coupled pair, you may need to increase the length slightly, because in many of these modern processors, the flicker noise is a stronger function of length compared to the width. Okay, so you will find that you need to increase the length slightly. That is also possible. Now, finally, you need some tuning to make it a true voltage controlled oscillator. You can start off with replacing the full capacitance with varactors, but if you do that, there will be a noise penalty, because your KVCO is going to be very large, and any amplitude noise will get converted to phase noise. Okay, the larger the KVCO, the larger the varactors, the larger the KVCO, and you will see more noise. Okay, unfortunately, if you actually start off designing this way, normally the simulator gives you a noise summary to tell you which source the noise comes from. But something like this AM to PM conversion, it will tell you the source of the noise, but unless you understand why it is coming about, you may be completely lost. Okay, that is why I wanted to make this particular point. Therefore, what you are going to do is you are going to get a small portion which is going to be continuously tunable using a varactor, but there is the larger portion of the capacitor is going to be a fixed capacitance with switches in series. And you are going to get an optimum value, optimum trade-off between the Q of the capacitor bank versus the Cmax by Cmin, the tuning range offered by the capacitor bank. Okay? And remember, these things are fraught with a lot of issues. The minute you do this, you need to make sure you have full frequency coverage, right? The minute you add these kinds of binary weighted capacitors, you need to make sure that this fine-tune range of the VCO covers every possible frequency over the range of frequencies that you want. If you want the VCO to tune, let us say between 2.3 to 2.6 gigahertz, okay? If your, let us say if your KVCO is, let us say 30 megahertz per volt, right? How many steps do you need? You need 10 steps, first of all. Assuming that the power supply is maybe 1.2 and it tunes over 1 volt, right? So with a single varactor for each step, you can tune 30 megahertz. You need to cover 300 megahertz. You need 10 steps. You need 10 coarse tuning steps. That's clear, right? And among those coarse tuning steps, when you tune, when you turn on and turn off these switches, you need to make sure there is overlap in the fine tuning, right? Otherwise, you might find a dead band where the PLL may never lock, right? So these are all, practical issues. We don't cover it in this course, but if you ever design a VCO, you will have to take care of these. Okay? So, so much for the cross-coupled oscillator. So in today's class, I'm hoping to finish up, oscillators completely. We will deal with the single transistor oscillators in today's class. So these are slightly more specialized applications, maybe either a discrete kind of oscillator where you want to limit the number of transistors and so on. You may not have a very large tuning range to meet. In such an application, you can use a single transistor oscillator. Of course, you can ask a good question as to why you can't use a cross-coupled. One primary reason is if you're building a discrete oscillator, it is quite difficult to get two identical transistors, right? The whole idea of a cross-coupled pair is that the two transistors are identical and you get a differential output, right? If you have a discrete application, this may not be possible. However, people have also ended up making IC-based versions of this, of these single transistor oscillators. So let us see where this leads us and actually how you start. So let us say you want to build a single transistor oscillator. We will again start with the negative resistance model. Okay, that is quite often easier to analyze. So what we'll do is we'll take a single transistor and I'm going to do something. So I'm going to connect a capacitor between the gate and source and the drain and source. I'll call this C1 and C2. Okay, and I'm going to look at the input impedance between the gate and drain nodes. Is that clear? I'm going to take this particular configuration. I'm going to look at the input impedance between the gate and drain nodes. How do you do this? You apply a test voltage, find out the test current, divide the two, and you will figure it out. So, for example, so I have C1, I'm going to apply my test voltage which is Vt, and I have a certain current It here. Okay, so this is the gate, drain and source. This is my source node, and between the gate and source I also have C2. Okay, what is this? It's GM-VGS, right? So now I'm going to call this voltage V1 and this voltage V2. Okay, so this is GM times V1 minus V2. Okay, what is this voltage? The drain voltage? It's V1 plus Vt. Correct? And now, I mean, you put in these conventions, you can start writing out the equations and figure out what the impedance is. this is so straightforward that I'll just give you the final answer. So Z in is Vt by It. So this has three portions, so you get Gm. First let's look at the Laplace domain. Gm by S squared C1 C2 plus 1 over S C equivalent. C equivalent is C1 C2 over C1 plus C2. Okay, so this is what the input impedance looks like. So there is a capacitive portion and there is a second portion which is frequency dependent but has a negative resistance, because this S squared term in the denominator will give you a minus negative term. Okay, so your Zn of j omega will be minus Gm by omega squared C1 C2 plus 1 over j omega C equivalent. Okay, so your equivalent circuit looks like this. Okay, it looks like C1 C2 over C1 plus C2, and this is some minus Gm over omega squared C1 C2. Okay, how do you make this into an oscillator? Well, first of all, you add an inductor across these two nodes. Okay, that will resonate with this capacitance. Okay, and you also have a negative portion, negative resistance portion, which can compensate for the losses, right? So suppose I take this oscillator, rather I take the circuit C1 and C2, and okay, I am going to connect some L between these. So what do you know? So if I call these the oscillation nodes A, B, two things you know. If you were to represent this as a, you can easily decompose this into a parallel equivalent circuit, right? What you do know is that the negative resistance should be greater than or equal to, less than or equal to the positive resistance if you look at them in parallel. Okay, so the oscillatory condition is very straightforward. So the magnitude of this minus Ra, okay, should be less than or equal to the positive portion of the resistance across AB, right? That we know. And of course you can also get the condition for oscillation, the frequency of oscillation and so on, right? Obviously the imaginary part of the impedance should go to 0 at a particular frequency. That is pretty straightforward. Now what is more interesting for us is that so far we have been looking at the signal picture. We have not grounded any particular node, right? We have just been looking at these two nodes relative to each other. Now depending on different bias conditions, or rather depending on which terminal you actually ground, you can get several different kinds of oscillators. Okay, we will take the one case. We are going to ground the gate terminal. Okay, if you ground the gate terminal, okay, and this other end of the inductor is also grounded, what do you have? You have C1 and you have C2. Okay, so this, again I have not shown the biasing, I have just applied the ground at one terminal. How would you bias this network, or how would you bias this circuit? Correct. So first of all you need to have a bias current for the transistor, so you will need to add a current source here. What else? Power supply needs to go in, and power supply can actually go in here, VDD, and you have an oscillator circuit, right? the circuit will oscillate, and this particular circuit is actually a very popular circuit. It's called the Colpitts oscillator. Yeah, sure. That's right. I didn't talk about that. You have to apply some VB here. Absolutely. You have to bias the gate also. Okay. So this particular oscillator is called the Colpitts oscillator. Similarly, you can, this is one example. You can bias the source and the drain, and you will get different versions of the oscillator. We will particularly look at this particular oscillator just briefly, because this happens to be the most popular kind of popular topology. But yes, sure, of course it is. Okay, actually, if you look at the parallel to series conversion we did, we just operated on on the Q, and in terms of, and the Q we just defined it as a ratio of the imaginary to the real part. Right? It doesn't matter whether it is positive or negative. We just did a bunch of algebraic transformations, that's all. Okay? So, again, if you needed to design this Colpitts oscillator, the design equations governing this oscillator are very different from that of the cross-coupled oscillator. Okay? And we will probably not go through this. Okay? The main thing to note, there are a couple of things you need to note. First of all, you see this portion. Right? Instead of having an explicit capacitance as you had in the cross-coupled oscillator, you had a single capacitor across the inductor. Here you actually have a tapped capacitor. Right? You actually have two capacitors C1 and C2. Right? And the actual equivalent capacitance across the tank is actually the combination, the series combination of the two capacitors. It's C1 C2 by C1 plus C2. Okay? The second thing to note is that this oscillator can also be very easily, analyzed using the feedback model. You are basically taking the oscillation across the inductor and feeding back a small portion. If you remember, when we did this impedance transformation, we briefly talked about tapped inductor and tapped capacitor matches. Right? This is basically a tapped capacitor circuit, okay, which is being used to feed back a certain portion of the oscillation signal back into the source of the transistor. The transistor gains it up by a certain amount, and then you get it. You can also look at this as a feedback oscillator. Okay, and there are many different versions. Actually, instead of having a fixed inductor and a tapped capacitor, you can have a circuit which actually has a fixed capacitor and a tapped inductor. Nothing prevents you from doing that. So, if I were to take the exact same thing, replace the capacitors by inductors, replace the inductors by capacitors. Okay, this is some C. So, sorry, draw it in a slightly different way. Okay. C, L1, L2, and I'm going to take the tap between the two inductors and feed it back. Obviously this looks slightly different because of biasing details, right? Because I need the DC current to pass through the inductor, so the inductor actually has to be connected to VDD, unlike the capacitor which could just be connected to ground. But it's basically the same circuit, right? This particular oscillator is called the Hartley oscillator. Okay? Obviously, once one particular version has come up, you can actually come up with many different versions of this. Similarly, there is nothing which prevents you from having just a single tap. Right? Right now we are using L1 and L2. Or if you go back to this, we have C1 and C2. Okay? Now, the fundamental limit on the output amplitude depends on the transistor going into triode region, or breakdown concerns with the devices, mainly the transistor. suppose you want to achieve, very large amplitudes for phase noise reasons, right? You can have a tank which has more than one tap, which has two taps, and one tap actually feeds to the drain of the transistor, the other tap actually feeds to the source of the transistor. So the actual oscillator has a much larger amplitude, but the signals you actually feed back to these two nodes are smaller. That is also possible. Here we have actually connected the tank at the drain itself, so that the full amplitude of the tank appears at the drain. That is not necessary. Okay, and in fact that kind of oscillator has also been designed before. It's called a clap oscillator. Okay, so similarly, you can have many different configurations with certain advantages. Okay, but I mean, since due to lack of time we are not interested in giving a catalog of oscillators. If you are interested, I would encourage you to go ahead and read the the Thomas Lee textbook that we have given as a second reference. He does have a good list of oscillators which have been used before. Okay, so but what we need to understand is that there are several different kinds of oscillators. Do you have to use a tap? What other methods of feedback do you know? You can use a transformer, right? Instead of using a tapped inductor, you can actually have a third version which looks something like this. So give me just a second. So I'll say C, and let's say I have a transformer here, maybe like maybe an n:1 transformer. Alright, you need to go down, remember. You need to feed a fraction of the signal back. Instead of using a tap structure, you can use a transformer. Right? The main reason why you are actually using a transformer, right? There is a very fundamental reason why you need to use this kind of downward transformer. Okay? Of course, fundamentally the amplifier actually amplifies the signal, so you only need to feed back a portion of the signal. But apart from that, if you actually look at the input impedance here, what is the input impedance here? It looks something like 1 over Gm. Obviously you have some impedance looking up at the drain, but assuming that the transistor output impedance is large enough, okay, the input impedance looking in here is very close to 1 over Gm, which is normally very small. Okay, if you directly connect it across the tank, your oscillation condition will be completely destroyed, because you are unnecessarily loading the tank. Okay, your loaded Q would be much smaller compared to the unloaded Q. Okay, that is why you need an explicit impedance transformer. The impedance transformer you can achieve using tap structures or using transformers. Okay, now apart from this, there is one more aspect which you need to understand. So we will just consider the Colpitch oscillator as an example. So let us say I take this Colpitch oscillator, and this is your IP, let us say, and you have this capacitor C1 across from the source to ground. Okay, so now what we are going to say is the drain node well, depending on what configuration you are using, really, right? If you actually look at the current through the transistor, okay, this is really independent of which configuration you use actually, but we will take the Colpitch oscillator as an example. If you look at the current through this oscillator, okay, and plot the voltage and current waveforms. So this is the voltage across the tank as a function of time, and this is the drain current of the transistor. What you will find is this: of course the output signal needs to be a sinusoid. If you look at the current through the transistor, what do you expect it to be? In the case of the cross-coupled oscillator, the current through each transistor was actually a square wave. Okay, in this case you have a single transistor, And if you plot the current through this, okay, the current looks something like this. Actually, even more explicit. Okay, as it so happens, there is a spike of current, there is an impulse of current at the peak of the voltage waveform. Okay, and at all other times the current through the transistor is zero. In fact, what you call as the bias current is the average value of this current spike. Okay, again, if you want more details about how to understand this, why this happens, go ahead and read Thomas Lee's. It's a very straightforward way to derive why this happens. Okay, but the reason I am covering it here is to tell you something very important. Because the current spikes at this point, okay, and the current spikes are coincident with the peaks of the voltage waveform, you will find that the noise from the transistor is also injected at these points. Obviously the noise depends on the current through the transistor, right? And you will find that noise is also injected into the tank from the transistor at these exact points. Okay, what do you know about noise in an oscillator? You inject it at the peaks of the voltage waveform. They have very little effect on the phase of the oscillator, right? In other words, such an oscillator has the potential to have very good phase noise performance. Okay? Okay? So because of this means this can have very good phase noise performance. Okay, and fundamentally you do find that the ISF of such an oscillator is different from that of the cross coupled oscillator, and people have observed better phase noise. What is the drawback with such an oscillator? Can you think of any drawback? Well, the most important drawback is that it does not give differential outputs. Okay, if you look at most modern IC based circuits, you try as much as possible to implement differential circuits because you are sensitive to so many things which are feeding in from the substrate or from the supply or from the ground, right? So if you want to build a differential version, it is not so straightforward, but people have done it. Actually, as it turns out, after you do it, it seems more straightforward, right? But it was not done for quite a bit of time. Until recently, maybe 10 years ago, people came up with a differential version of this. Now the funny thing about the differential version is it actually used a cross-coupled pair to actually make the differential version. Okay, it's quite funny. So that is what they needed to do to make this differential. And what people have found is that this does have slightly better phase noise. Unfortunately, it also has much lower tuning range compared to the normal cross-coupled oscillator. Okay, so because of that, this is not a very popular architecture. There may be very specific cases where you have a very narrow band of frequencies to cover, but you want very good noise. You might go in for something like this. Okay, but apart from that, a majority of oscillators are still cross-coupled oscillators. Okay, and you can read Thomas Lee's textbook for the startup condition and so on, or you can look at the lectures from a couple of years ago where I have covered it. The other part we need to understand is if you have to compare this oscillator with a cross-coupled oscillator, how would it perform, right? And that comparison is also given in the previous year's lectures. So I just go ahead and look it up if you want to understand it very well. Okay. Now, yes. Okay. Yes, that's what people do normally. But what happens is, fundamentally that is the reason, right? To get the same amount of negative resistance, you actually need to have a much larger transistor compared to what you need in the cross-coupled pack. Okay, that is primarily why you will see a major hit in tuning range. Okay, really the overall tank capacitance is actually C1 parallel C2, C1 series C2, so it should actually be smaller, right? But the parasitic capacitance is much larger. Second thing is, remember, there is another reason. When you feedback this signal from the drain node to the source node, you want the ratio of capacitors to be C1 by C2. Okay, unfortunately, you also have the CGS of the transistor between in parallel with C1. Okay, which means to actually get a good feedback factor, C1 needs to be much larger than this CGS, and therefore C2 needs to be much larger than CGS. That is another reason why your tuning range will be cut down. Okay, so with that we kind of come to the end of the oscillators chapter. Now for like maybe 10 minutes or so, I just want to discuss quadrature generation, because one of the other things we need to discuss is that you have the VCO, but we said the VCO gives you differential outputs, but if you want a mixer, especially maybe a single sideband mixer, you actually need 0, 90, 180 and 270 phases. You need 4 phases, right? So now we need to figure out how to generate those 4 phases, and there are some very common techniques used. Okay. So the first one is very similar to something we have already seen before. So what have we seen before? So if I take this guy, okay, any signal, okay, in fact I don't even need to do it this way. So I take a particular signal, okay, and what do we know about this circuit? We have seen this circuit before. It splits into plus 45 degrees and minus 45 degrees, right? Okay, we have seen this for quadrature generation. Now we saw this as part of your the image reject architecture, right, in receivers. Now we just have to extend this to actually generate differential versions of both the 0 and 90 degrees. So you need 0, 90, 180 and 270, and as it turns out, so let's say this was 0 and 180 degrees. I buffer it up. This is your VCO, so I buffer it up, and let me just draw out this circuit. Okay, something like this will actually give you minus 90 degrees, 0 degrees, 90 degrees and 180 degrees. Okay, we have just extended the same thing. Instead of using 2 RCs, we are going to use 4 RCs, right? We are basically going to split each one of these guys 0 and 180 into plus or minus 45. Okay, this can easily give you 0, 90, 180, 270. What was the fundamental problem? This is called a polyphase filter, by the way. what was the problem with the polyphase filter? We have seen this earlier. You can get duty cycle errors. Now, apart from that, there is a second problem. Okay, when you actually design, these kinds of polyphase filters, you will have to choose the value of R's and C's, right? All we have seen so far is that, you have an R and a C, and you choose it for a certain thing, plus minus 45 degrees, and you know that the amplitude matching happens at a certain point. If you double the R and half the C, you will get the exact, the same performance. The difference is, the R tells you how much loading you have on the previous stage. Okay? The C tells you how sensitive you are to capacitive parasitics. Okay? And therefore there will always be a trade-off in this particular architecture between the amount of current you burn versus how sensitive you are to parasitics. Now, there is a trade-off, we said there is a trade-off between loading and what? Parasitic capacitance. Okay? So in other words, if I want to use such a polyphase filter to operate at, let us say, 5 gigahertz instead of 900 megahertz, the first thing I'll have to do is I'll have to make these capacitors much larger, because the parasitic capacitances are much more dominant at higher frequencies. Because what happens is, to get it to operate at 5 gigahertz, already the capacitance will be much smaller. If you use the same resistance, the capacitance will be much smaller than if you had done it at 900 megahertz. But now what I'll have to do, I'll have to reduce the resistance and increase the capacitance so that it does not depend on parasitics. If I do that, I'll just have to burn more current to get the same bandwidth or the same loading, to take care of these loading effects. Okay? Okay? Higher current at higher frequencies, if you want to compensate for this parasitic capacitance. So what you'll find is, this kind of polyphase filter was popular, for a long time, but then eventually people stopped using it, because there is a much easier way to get this done, much more robust way, which actually, uses a frequency divider. Okay? So the way to do this is, I'm going to take a D flip-flop. In fact, I'm going to take two D flip-flops, and these D flip-flops have to be differential, because you want to get differential 0, 90, 180, 270. So you want to get differential quadrature signals. So let us say the inputs were D and D bar, D and D bar, and the outputs are Q and Q bar. Okay? And I had clock and clock bar. Okay? So this is a completely differential in all respects. This is basically a divide by 2 counter. Okay? Except I am using differential flip-flops. This is going to operate at a very high frequency. Okay? If you actually look at the output, if I call these 0 and 180 degrees, then the other outputs will be 90 degrees and 270 degrees. Okay? I'll get all 4 outputs from the same circuit. And it's, if you look at these modern processors, it is very easy to build a divider operating at these kinds of multi-gigahertz frequencies using only a moderate amount of current. Okay? By just using a few milliamps, you can actually get very good performance all the way up to several gigahertz from these kinds of processors. So the difference between this one and the polyphase filter is that the VCO frequency there needs to be the same frequency as here, as the output, as the LO frequency. Here it needs to be double. Now the difference is, once you have decided that for pulling you want to go ahead with move the VCO and frequency, then this is a natural winner over the polyphase filter. Okay? Because we said that if the VCO is the same frequency as the transmitter, you are going to have pulling effects. Okay? If you want to prevent that, you anyway want to move it away. So 2 or 4x, makes, it's actually a very good decision to do anyway. Okay? So the third way of generating this quadrature signal is actually by using what is called a quadrature oscillator or a quadrature VCO. Okay. What do I mean by a quadrature oscillator? So there are ways to actually take two VCOs, okay, and couple them such that the two outputs of the VCOs are at quadrature with each other, are at quadrature phase with each other. Okay. Now there are obviously, several different ways of coupling the two oscillators. Okay. People have thought about several different ways. You can take the output of the first one and then couple it to the input of the other one, such that the two oscillators, you can prove that the two oscillators will always be in quadrature, because if they are in phase or out of phase, you can show that the oscillation will die down. Okay. Again, I don't need to cover it here, but you can actually go back and look at the notes to see what the exact architecture. It's a very straightforward architecture. Similarly, people have actually taken the second harmonic, okay, and then coupled it appropriately such that the two oscillators are in quadrature. Okay, because remember that the VCO is a symmetric circuit. Okay, so at the outputs you will have the first all the odd harmonics, but at all the common mode points you will have the even harmonics. Okay, and that even harmonic will have a very specific phase relationship with the output of the oscillator. So if you take the two second harmonics and couple them such that the two oscillators are in quadrature, they will naturally settle down at quadrature with each other. So that has also been exploited. There are other ways of injecting signals from one oscillator into the other to actually get them to lock in quadrature. But I just wanted to quickly point this out. Okay. So first of all, if I were to design, let us say I want a quadrature signal at 20 gigahertz, right? What do I have to do in the second case? Look at it. Okay, let's compare all three. I want to get a quadrature LO at 20 gigahertz or 40 gigahertz, right? What would you do with the first case? You probably can't even get it to work. Okay, because the values of R's and C's which you will want will be, so small, you probably can't even get it to work. Let's look at the second one. What do you have to do in the second one? You need an 80 gigahertz oscillator. Okay. Apart from that, what do you need? You need a divider operating at 40 gigahertz. That is also quite difficult. Okay. It is possible because now you need to move from the traditional CMOS kind of either dynamic or static CMOS kind of architecture for these latches to look at maybe inductively loaded current mode latches. Okay. That will also consume a current and area. Well, if you were to do that, you might as well use two VCOs. They will operate at your frequency of interest. Okay, you don't need any extra dividers, and you probably use the same amount of current or even lesser compared to the other one. Right? So there are each one of these techniques can be used with certain kinds of systems in certain situations. Okay, so that is the important thing to remember.